Here's circuit number one. This is our very first circuit that we're going to build in falstad. And the great thing about this circuit simulation very much prepares you for the hands-on circuits you're going to do in class. So this is probably one of the most popular engineering applets out there. Falstad circuit, very widely recognized, and it's great. And you'll hopefully agree. But here's our first circuit. Circuit number one that you're looking at on the screen. Circuit number one. This is a simple series circuit with 4 elements: a battery, a wire, a resistor, a ground. So we're going to build that right now in falstad circuit and then talk about it and take a snip of it. So if I go to falstad circuit, and again, please speak up whenever you have any questions or use the chat box amongst yourselves. But first thing I'm going to do is hit circuits blank. Circuits blank. So there's a brand new slate, brand new piece of paper. And I'm going to remember what I'm doing. This is my circuit. So battery, resistor, ground. So I guess we'll start from the left and work rightward. All right. So right click anywhere on your workspace and say inputs and sources. Inputs and sources. Oh, the other thing before we get into the nitty gritty. Circuits, blank circuit, as mentioned. Here's what I do. I recommend options, and then put a check mark next to the show cursor crosshairs. I think that just makes it really easy to create circuits. So again, you're clicking options, show cursor crosshairs, right click. All right. So now that you've done that, right click anywhere on your workspace, and then under inputs and sources, let's select add voltage source to terminal. Click. And then here's how you create a battery. You go from the bottom up. There it is. That's my battery. Let me do this. I'm going to go through this, rapidly. Then I'll do it over again and maybe over again and just, repetitively. And then you guys, again, talk to each other in the chat box, unmute your mic and ask me questions. I'm going to do a wire. Right click anywhere on your workspace, select add wire. There's my wire. And then it's time for the resistor. Right click anywhere on the workspace, add resistor. There's my resistor. One more wire, add wire, add wire. So there's my circuit, and you can see the electrons are flowing. And these are technically, they're not electrons. These are positive charge carriers, because the convention is whenever we indicate current direction, we always assume a positive charge carrier. I'm going to create a ground, which is like a reservoir. Right click anywhere on your workspace. This is inputs and sources, add ground. And then it's like this little Christmas tree right there. And this ground is basically a reservoir. It says, hey, if there's too much electricity, I'll take the excess. And then it says, hey, if you're kind of running low on electricity, I'll give you some. So it's just like not just like, but it's very similar to like a water reservoir or a heat reservoir in thermodynamics. So there's our first circuit. I'm going to go through and just start all over. I'm going to click circuits, blank circuit. And the first thing I'm going to do is create that battery, right click anywhere on the workspace, select inputs and sources, add voltage source to terminal. So it's that second one, add voltage source to terminal, and then click and hold bottoms up. There's my voltage source. Then I'm going to create a wire, right click anywhere on your workspace, add wire. Done with the wire. As long as I'm in wire mode, maybe I'll do something bold and different, and I'll create the bottom wire down there. Okay. And then I'm going to create my resistor. Right click anywhere on the workspace, add resistor. There's my resistor, all snapped into place. And then last but not least, my ground, my little upside down tree, like that. Okay, so that's it. You're looking at our very first circuit. It looks just like this. We just have to set up values now. This is a 5-volt battery and a 1,000 ohm resistor. So back to falstad. All right, so how do I set my 5-volt battery? Double click on the battery, double click. So put your cursor right on top of the battery. That long line is the positive terminal. The short line is the negative terminal. Double click and specify 5 volts, which is the default, but just what if it wasn't? 5 volts DC, direct current. Say, okay, so that's my 5-volt battery. And this is a 1000 ohm resistor, which again is the default, but what if it wasn't? Just double click on the resistance, on the resistor, and you would just change. You could actually type in 1000, or you could, it recognizes prefixes. So you could just say 1K. There it is. This is our very first simulated circuit. It's a series circuit with a 5-volt battery and a 1000 ohm resistor at the ground. All right, so let's go ahead and what do we have? Let me just take a look at our reference here. We need to display this information. So I guess in falstad, if I put my cursor on any wire, will that work? No, I guess if I put my cursor on the battery element. So I'm putting my cursor on the battery element. And you can see the bottom right of my screen. Make sure I'm sharing what I think I'm sharing. All right. So hover your cursor over the battery, and it says, "Hey, you're looking at a battery, and the current going through this battery is 5 milliamps, thanks to Ohm's law, which we'll get into. The voltage drop is 5 volts, and the resistance that's in this circuit is 1 kilo ohm, and the power is negative 25 milliwatts. That means the negative means this is a source. This is the source of energy. It's not a sink, it's a source. That's it. That is our very first battery. I'm sorry, very first circuit. Let's do this. Let's take a snip. So I'm going to do Microsoft logo Shift S. I'm going to take a snip of this circuit, and then I'm going to go into a blank Word document or Google document. If you use Google Docs, then you'll just have to print out a PDF, which is fine. But I'm going to go to a blank Word document. There's my blank Word document. And then before you paste anything in, go ahead and let's provide a header. Wait for it. Okay. All right. So let's give us this as a header. This will be called falstad, or sorry. Let me fix this. All right. This should have been, I should have said, this is the chapter 27 quiz for falstad circuits. And then you can do physics 212-14, and then you can do your first name and your last name. So that can be the header. And then let's maybe space things out with tabs or however you want to do it.
Professor Wood, all I'm seeing is a close-up of a screenshot of the falstad circuit.
Okay, there you go. Thank you. So this is the header. Chapter 27. All right, so with this, and then maybe let's put it in a box. So let's put a box around it. And I'm going to look for this too, you guys, because every so often formatting is important. So if you have any questions about formatting, it's fair game. Those questions are absolutely fair game. So chat amongst yourselves in the chat box or unmute your mic and let me know how I can help you. But right now, I'm just making this look okay-ish. That is okay-ish. Okay. That's my header. And then below this, you can go ahead and do paste. That's circuit 1. And then we don't have to take up all that circuit. We don't have to take up all that screen space. So there's the circuit. And then the next thing I'll do is take the meter. So I'm going to go back. I'm going to go back to falstad circuit. highlight my battery, and then I'm going to take a snip of that data box right here and be done with it. That's circuit number 1, data box, and then back to there. This is circuit 1. Circuit number 1. Falstad circuit number 1. Falstad circuit number 1. Okay. Let's get ready for circuit number 2. And let me just keep repeating my my announcement. Feel free to chat amongst yourselves in the chat box, or if you want to talk to me, unmute your mic and speak up like Luke did to alert me that I'm talking to a different screen. Falstad circuit 1 is in the box. All right.
How did you get that data box to the right?
I went into Falstad, and then I hovered my mouse over the battery, and you can see it pops up on the screen in the lower right of the Falstad simulation window. And then I did Microsoft logo Shift S, and I took a snip of it, right like that. And then with this snipped, I went back to the Word document, and then I just pasted it right next door.
Okay, thanks.
Yep, good question. All right, so done with circuit 1. Let's do circuit 2. Before we go to circuit 2, this is a series circuit. We're doing more than just making fun pictures. But one of the big takeaways of this is hover your mouse over any wire. And when I put my mouse here, my cursor here, it says, hey, there is a current of 5 MA, lower right window. Notice on my lower right window, when I put my cursor on this wire, it's 5 MA, which stands for 5 milliamps. And then put it on the top wire, 5 milliamps. Put it on the right wire. Put it on the right wire on top of the resistor, 5 milliamps. So everywhere, no matter where I analyze this circuit, no matter what circuit element or wire I analyze, it's 5 milliamps everywhere, because this is a series circuit. There's no branch, there's no fork in the road, there's no off ramp or on ramp. Whatever goes through any element is going through all other elements, because there's just a single loop. Simple series circuit. That's circuit number 1. Here's circuit number 2. Done with circuit number 1. 1 down, 2 to go. Circuit 2 looks like this. Okay, 3 resistors in series. So you know what I'm going to do? I'm just going to go back to Falstad. And just because I always enjoy spring cleaning. So I'm going to click on circuits blank. Circuits blank, and I have a battery with 3 resistors, 1, 2, 3, and a battery underground. All right, so I'm just going to do those 3 resistors in a battery. Here goes. Right-click anywhere in your workspace, select Inputs and Sources, add voltage source to terminal, and bottoms up. Okay, that's my battery. Right-click anywhere on your workspace, select Add Resistor, and there's resistor 1. And then I'm in resistor mode, so I don't have to keep specifying resistor. There's resistor 2. And last but not least, here's resistor 3. And now I'm going to just select a ground. Right anywhere on your workspace, right-click, Inputs and Sources, add ground, and you are done with the basic construction. Now, as far as values are concerned, this is circuit number 2. The battery is 5 volts, which is the default. So I have 900, 300, 600 for my resistors. 900, 300, 600. So back to Falstad. Double click on the top resistor, 900. Double click on the right resistor, 300. And then double click on the bottom resistor, 600, 900, 300, 600. and double click on your battery. And we know it's supposed to be 5 volts, which is the default, but just to be attentive to detail, this is a 5-volt battery. So it is a 5-volt battery. That's it. So now I know one thing. I know this is a simple series circuit. So I know that the current everywhere is going to be the same, 2.778 milliamps. It's the same everywhere. So that's the sanity check. That's the sanity check to ask and answer the question, is this a series circuit? And it is a series circuit because the current's the same everywhere. And obviously you can look at it. One other thing, I think, let's do this, a little variation. All right, so I'm going to do this. I'm going to just draw a little selection box. I'm going to I'm hitting the escape key so I get out of drawing mode. And I just want to, I'm just going to select my whole circuit right here. And I'm just going to move it to the left, get it a little bit to the left. All right, because these are 3 series resistors, I know I can combine them. I just stack them. 900 plus 300 plus 600 is 1800. So let's do this for the sake of experiment. I'm going to create, in fact, maybe I could just copy and paste. I'm going to draw a zoom box around this entire circuit that I've moved to the left. And then I'm going to hit Control C for copy and then Control V for paste. So there's a pretty quick way of making a copy and paste of this circuit. And now I want to just cough up. I want to create a circuit that's equivalent to this with an equivalent resistance. Because this is a simple series circuit, I'm going to replace these 3 resistors with an equivalent resistance. 900 plus 300 is 1200. 1200 plus 600 is 800. So you know what? I'm going to get rid of this. Get rid of that top wire. Get rid of that top resistor. Replace it with a wire. Get rid of the bottom resistor. Replace it with a wire. Now I have to be careful of these nodes. I can only connect to nodes. I just can't connect to a wire anywhere. It has to be to a node, like a snap 2 point. And then change the resistor value of this 300 ohm resistor to 1800, which is the equivalent resistance. So these two, in many ways, these 2 circuits are identical in terms of their equivalent resistance. The one on the left is the same as the one on the right. How can we sanity check that? Put your cursor anywhere on the left circuit. No matter where I put my cursor, I'm getting 2.778 milliamps. I get it there. I get it there. I get it there. And then here's the test. I'm going to do the same thing with this circuit, 2.778 milliamps. So the equivalent resistance is equal between the left and the right. The voltage source is equal, and you can see the resulting current is also equal. So let's just do this. Let's take a snip, Microsoft Shift S. Let's take a snip of both of these circuits, and then let's go to Microsoft Word or Google Docs. And this is falstad circuit number 2. Doesn't need to be that big, so let's scale that back, perhaps. And then I'm going to go back to falstad, and I want to get a snip of that little data window. And the reason I'm doing it separate like this is to avoid taking a screenshot of that whole gigantic. Although, you know what I could do? Here's some innovative thinking. This might be better. Look at this. Look at my thinking. I'm just going to cram things down here. And this might save just a bit of toil and trouble. So just getting things conveniently located, and that's probably pretty good. So this would make for a very good snip right here without having to do a 2-step process. So I'm taking the snip of my 2 circuits in their entirety and including just the part of this data window that I need. And then that's what I can put into Microsoft Word. So that is, I think, saves a step or 2. And once again, I don't need all of that. Let's get ready for circuit 3. And again, if everyone is keeping up, that's good. I'm sort of assuming there's nothing going on in the chat box, and you guys have asked a couple of questions. So if there's no ongoing conversation. That means you guys are completely tracking with me because this is going to be due kind of as soon as we're done. All right, so let's do circuit number 3. Circuit number 3, 2 down, 2 to go. Here's circuit number 3. This is a parallel circuit with the same resistors, 900, 300, 600. So this is circuit number 3. I'm just going to do circuits, blank circuit, and just go from the beginning. Right click anywhere in your workspace, inputs and sources, add voltage source to terminal. There it is. And then my next resistor, it's in order, it's 900, then 300, then 600. Okay, so right click anywhere in your workspace, select add resistor. And then this is one of the resistors, and I'm still in resistor mode. This is the second resistor, and this is my third resistor. And then I'm going to switch from resistor mode to wire mode by right-clicking anywhere on your workspace, add wire. And I can't do this. So this would be a mistake, you guys. What I just did would not work because technically speaking, these two resistors aren't connected to that top wire. So I have to go from node to node to node. So that's a common mistake. I mean, it certainly looked like I wired it up correctly, but well, actually here, well, let's finish this. Node to node to node. And then let's put the little upside down tree known as the ground, which is just a reservoir. Inputs and sources, add ground. There it is. So now let me just go back and make my mistake on purpose. What if I had everything as you see here, and I wanted to connect my wire like this, add wire, and I just went from this left node all the way to the right, like that. You can see there's no current flowing through the interior resistors. So they're just sitting there. It's as if they're not part of the circuit whatsoever. They're completely invisible to the circuit because they're technically not connected. You have to connect at node points. So right click, add wire, node to node to node. And then there you are. And then 5-volt battery. I'm just going to check. Is that 5 volts? I'm just hovering my mouse over it. Yes, it is. And then it was in order 900, 300, 600. So ready, set, go. Double click 900 for the left, 300 for the right, 600. I'm sorry, 300 for the middle, 600 for the right. That's it. So now this is different. These are 3 resistors in parallel, which means I've got branching. Check this out. Look what happens when I put my cursor right here. I have 30.566 milliamps coming out of my battery. So my circuit current is basically the current that's being fed into the circuit. My circuit current brought to you by my battery, my voltage source, is 30.556 milliamps. Okay, but put your cursor anywhere on the leftmost resistor. Is this 30.556? No, because I have branching. I've got a portion of my current that branches into my 900 ohm resistor, 5.556. And then I've got another portion of my circuit current, which is again flowing out from the battery into my middle resistor, 16.667. And then I also have the other portion, or the remaining portion, that's branched out to my 600 ohm resistor, 8.333. Okay. So this is it. This is, you're looking at the difference between parallel circuits and series circuits. With this parallel circuit, I have this branching. One thing I should have done with the other one, but I can bring it back. Here's my voltage source. 5 volts. I'm still remembering par V, PAR hyphen V. Par V means stuff that's in parallel has the same voltage. So everything here is in parallel with everything else. So every element you see on this screen should have 5 volts. Let's check it out. Put your cursor on top of the battery. It says VD, which means voltage drop 5 volts. Then hover over to the 900 ohm resistor. It says VD 5 volts. And everywhere, every element I hover over, everything's different except for one thing. The voltage is different. I'm sorry. Everything is different except for one thing. The voltage is common. The voltage is 5 volts. So that looks pretty interesting, I suppose. So let's bring this down to, I'm going to hit escape. So I'm going to hit escape. I want to get out of circuit element drawing mode and just into pointer mode. So hit escape. So my cursor is going to change from a crosshair to an arrow. Highlight, just draw a zoom box around your whole circuit. And let's bring it down here. And then just hover your mouse over the battery like that. And this will be circuit number 3, where you're taking the circuit and just the data block and nothing else. So we don't need to include a whole bunch of dead space. And then go to your Word document. This is falstad circuit 3. And it looks like I'm going to spill over to another page, which is okay, not the end of the world. So let's do falstad circuit 4. Falstad circuit 3. Okay. So now it's for falstad circuit 4. Last but not least, this is what circuit 4 looks like. Interesting, huh? Actually, okay. Okay. Let's build this. 1, 2, 3, 4, 5, 6. 6 resistors. Okay, so just with this picture in mind, 3 on top. All right, so let's do back to falstad. Circuits, blank circuit. Okay, right click battery. So hopefully this is kind of getting familiar. It's always hard at first. Add voltage source, parenthesis, to terminal. Here's my battery. Let's go into resistor mode by right clicking on your workspace and selecting add resistor. 3 on top. 1, then go node to node to node 2, 3. And then what do I need to do? This is circuit 4. 3 on top, 3 horizontal, 3 vertical. And then careful, I have to go from this node. So there's 1 node to node, 2. I'm snapping to the nodes. 3. And then the rest are just 3 wires. Right click, add wire. And that's it. Then I need my ground. Right click, inputs and sources, add ground. There's the ground. Now I just have to worry about values. I think the circuit is built correctly. On top, so across the top, it's 263. So double click, just 2. Double click on the middle resistor, the middle horizontal resistor, 2, 6, and then the right resistor is 3, 263. My vertical resistors are 4, 8, 5. And I say I have to move my ground. 4, 8, 5. All right. Leftmost vertical resistor is 4. Middle resistor, 4, 8, 5. And now I'm going to move my resistor And I'm literally just going to grab hold of it. Oh, not like that. I was still in circuit drawing mode. So Control Z to undo. Escape. All right. I guess I'm delete. I'm not Control Zing. I'm hitting the delete. And then I think if I hold down if I highlight the element and I hold down the Shift key, it lets me move it. So if I didn't hold down the Shift key and I tried to do that, if I just grab this ground and make sure you're in selection mode. So again, I had to hit the escape key, and the escape key takes me out of circuit drawing mode and just puts me into selection mode. And I know that because I have an arrow crosshair. And if I didn't hold down the Shift key, what happens if I try to move it? Oh, I guess it works without the Shift key. So forget that. This is good. Am I done here? My battery is 50 volts. So I got to change my battery to 50 volts. Back to falstad. Double click on the battery. The battery is 50 volts. Okay. So more complicated. This is a mixed. I have my 3 ohm resistor and my 5 ohm resistor are in series. So I could collapse those. 3 plus 5 is 8. I could replace this with an 8 ohm resistor. But for now, I'm just going to leave it as is. I'm going to make sure I'm in selection mode by hitting the escape key, select all of this circuit and bring it down to the lower right. And then put your, actually, I think we can do let's do a few more things here. Okay. Right click on your top left wire, right? Let me make sure I'm sharing. All right. Right click on the top left horizontal wire, right where you see me doing it. Right click, and then let's say edit. Hang on. I guess I want sliders. No, I might actually have to back off on what I was going to say, but let me try something. Edit. Let me experiment for a second. Edit. I want to get this is what I'm after, you guys. And I'm just kind of forgetting momentarily how to do it, but we'll remember. I want to get these numbers displayed as you see here. That 10 amp, 50 volts. I don't think I did that myself. So let's go back and figure out how to display. This is saying, hey, there's 10 amps going into resistor 2. This is saying there's 2.9 amps going into resistor 6 and 1.5 amps. Actually, for now, this will be good. We can leave it at that. All right, so we'll worry about that later because I don't need that. We don't need that here. All right, so once again, I'm going to bring my circuit. I guess right there's fine. And then Microsoft Shift S. Oh, before I do that, hover your mouse over your battery. So let me double check. My current is 10.294. That's circuit current. That's the current coming out of my battery, which is known as circuit current. And this is going to be interesting. It's saying my circuit resistance is 4.857. 4.857 must be the equivalent resistance. So if I take 3 and 5 is 8 and then collapse them. All right. So anyway, let's all just agree on these numbers. We're going to do that hard work coming up. But for now, highlight your battery element, Microsoft Shift S, take the circuit with the data as economical yet complete as possible. Go to Word, Circuit 4, Control V, done. Okay, so once you're done with that, make sure you have this header bar right here. I guess I'm going to add falstad to my spell checker. Okay, well, anyway, there. So there's your header bar. And once again, this has to be on the left side. This needs to be in the middle. This needs to be your first name and your last name. When you're done with all of that, do file, save as, save it to your local system, and then go into Blackboard. Let me make sure everything's ready to go. Going into Blackboard, when you're in Blackboard, go into our class, Physics 212, course documents, Chapter 7 quiz, 4 falstad circuits, and then attach your Word document or your PDF document with the header. Again, let me repeat. You need to have a header that and there's a reason why I'm going through all this, because I actually have to share these documents with other people. All right, but this is it. These are your 4 circuits. That's your header. Save it to a file, submit it to Blackboard, and onward and upward. If you have questions for me, let me know. If
Can you show me how you got the box for the header?
Yep. You know what I would do? I'm going to do this. This is probably the better way of doing it. Go ahead and do insert. Forget it. How I created the box. This is, let me turn that off. All right, so no borders. This is what you have spaced reasonably well. Left side. So this is your left side label, your middle label, your right side label, and then just double click, activate the whole thing. And then in Word, you can go under here. If you can see my screen, let me make sure. All right, yeah. All right. Highlight that line. And whatever you have activated or selected in Word, under paragraph, my little paragraph submenu here, menu block, you can just do that pull down and outside borders. And that's how you get a box around that. Yeah, so formatting questions are fair game. Being able to format stuff professionally is actually important. So I don't want to pretend it's not. And that's it. Chat amongst yourselves using the chat box, unmute your mic and talk to me, because now we're going to, let's see, it's 8:41. So I'm assuming you're done. Well, actually, I'll leave this up and we'll start quiz 1. Just if you need to, and then when we take a break, you can keep maybe working on it, but that is good to go. So now we can go to Wiley Plus. Wiley Plus, and the first quiz can now be unleashed. Wiley Plus, let me make sure. Chapter 27, quiz 1. Let me make it available. Chapter 27, quiz 1, just a second. This is a homework problem. So alert to everyone, not only is this a homework problem, but we're going to spend an enormous amount of time solving it. So you've got to change this. In fact, here, let me just keep nudging you, friendly nudge, you guys. This is your guide. So for those of you who are not happy with your exam scores, or maybe putting it a little more positively, for those of you interested in doing well on exams, this is your guide. So if you have the question, I'm kind of struggling with these exams, any ideas on how I can do better? Yeah, red, yellow, green, and stressing this days later. I mean, really, I think one of the key takeaways with this, preparing for this course or any other courses, and my favorite statement, if you want to do well on the job when you have to tackle new and complex challenges, attack early and spread out your attack over several days. So this is how you will do better in physics. This is how you will do better in your other academic courses. This is how you will do well on the job when you have to become an expert on something in the minimum amount of time. All right, so where was I? We are now doing chapter 27, quiz 1. It's now 8:44. All right, so this, I am going to intentionally take an enormous amount of time on this quiz because everything is in there. Almost everything is in there. All right, so you should see it. Let me know if you can't. You should see chapter 27, quiz 1. Please let me know if you cannot see it. And it should look like this. Okay. So we got the warm up with falstad, which is good. You're going to do a lot more with falstad, and you're going to do more than just draw pretty pictures. We're going to like use it for actual analysis, but that was a good, just wanted to do that as a kickstart. Here's chapter 27 at a glance, these 8 list items. So this is it. All of chapter 7, all of circuit analysis at our level is contained in these 8 summary bullet items, summary list items. So when you transcribe all of those chapter 27 green sheets, you're basically going to be filling in the detail for each one of these. So learn as you transcribe. So here is our very first circuit. In fact, what I want to do, the first thing I'm going to do is get a better picture. So I'm going to give me 1 minute to get a better picture, because again, this is a great problem to teach almost everything on that list. All right, it's just a copy and paste of what you see there already, just enlarged. All right, so we need to find out the battery voltage. This is our $ right here. We know the values of all those resistors, and we know the current going through resistor 6. And this is the $. It says, what is the EMF of the ideal battery? So just a note about EMF. This term EMF means electromotive force. This is going to be in your chapter 27 green sheets, but EMF stands for electro, there's the E, motive force, or EMF for short. An EMF is any device that creates a voltage. So think about it, you guys, in everyday life, what creates a voltage? And obviously a battery. A battery creates a voltage. What else can create a voltage? A solar cell. Solar cells create voltage. What else? An electrical generator. What else? A fuel cell. A fuel cell creates a voltage. What else? A thermoelectric device. What else? Maybe some other things that I'm just not thinking of right now. But there's a lot of things that actually create electricity, as opposed to voltage that is found across an element. So for example, this EMF, this battery, it looks like a battery. And remember the convention. So I'm going to really spend a lot of time on conventions. The convention is for a battery. This long bar represents the battery's positive terminal, and this short bar represents the battery's negative terminal, and it's actually labeled for you. This script E means EMF. It means, hey, whatever this is, it is actually creating voltage. There's going to be a voltage drop across each of these resistors. So just making up numbers right now because I don't know any details. Let's just say for the sake of conversation, there's a voltage drop of 6.26 volts across this resistor. This is not an EMF because a resistor does not produce a voltage. Although there is a voltage associated with this resistor, it's not an EMF, not an EMF. There's a voltage associated with this battery, and it's referred to as an EMF because it produces the voltage. All right, so that's our $. let me erase all of this stuff now, because that's the whole battery convention, and that's the introductions to what an EMF is, electromotive force. Okay, so it says we know the following. We know the current going through this far right resistor. It's 1.3 amperes. So this is going to require a lot of care. So keep your eye on your own work, and definitely keep your eye on me, and absolutely shout out when you see a mistake, because you're going to see a mistake, but because there's a bunch of us in this session, we're going to catch this mistake. So I6 is 1.3 amperes, 1.30 amp, and that's given. Another sidebar, AMPER, ampere. An ampere is defined as 1 coulomb per second, and we abbreviate the ampere as just A, which is, we did that lab last Thursday, and I didn't leave enough time for the lab, so I'm going to try to revisit it, because I hate labs like that. Well, I hate trying to rush things where everyone's like scrambling right up to the last minute. That's not a good way to learn. So I'm going to try to revisit it so we can maybe come up for air. But an ampere, this is an ampere. And then, so we have ampere is symbolized with current. So this is current, current. So I have some current. I have some current flowing through R6, and it's given for me. It's saying, hey, your current flowing through R6 is 1.30 amperes. And as long as we're here, current is defined as dq dt. Current is defined as the rate of charge flow. And you saw from falstad, you saw those little yellow dots. You saw those little yellow dots flowing. In fact, here, if I just, little sidebar, if I just went back to falstad, which is, I've lost it, but falstad circuit, if I just went back into this very quickly here, just to stress the point that I'm trying to make right now, you could see that if I just have a battery like this, here's my 2-source battery, and I have a resistor like that, and then wires. So check out the yellow dots. So those yellow dots that you see flowing, kind of looks neon-ish, that's current. These are positive charges, and you might say, hey, Chris, in reality, I think it's negative charges that flow through wires and batteries. And I would say, yeah, you're right, except this is just the convention we use. If you wanted to use, I think we have this choice. If I went under options, other options, is this a choice? Positive color. I think there's some setting here where I could change that, which I'm not finding it immediately. So who cares? Not that much. Positive color. Anyway, watch what happens when I crank up the voltage. I'm going to go from 5 volts, and then I'm going to go to 500 volts. Watch what happens to these yellow dots. 500. Crazy. So that's voltage. Remember, voltage is like water pressure. Voltage creates a pressure difference, and you're looking at a lot of dq dt right now is great. So that's just some comments about EMF and current and the ampere. All right, so I know one thing about R5. I know the current going through R5 is also 1.3 amperes. How do I know that? Because they're in series. There are no forks in the road. So I'm just going to do this little arrow here. And then here's IR5. Maybe I'll just call it I5. So let's just go ahead and call this. This is I6. This is I5. I5, I don't have to do any heavy thinking here. I5 is also 1.30 amps, because whatever goes through R5 must go through R6 and vice versa. because they're in series, no forks in the road. All right, so now I've got to do a lot of reverse engineering to go from all the way to the right to all the way back here, because we got to figure out what's that battery. What's the voltage of that battery to produce 1.6 amperes going through R6? All right, so let the reverse engineering begin. Well, here's one thing I'm going to do. What's my voltage? I'm going to deal with voltages now. What's my voltage across R6? So number one, the voltage across resistor 6 is brought to you by Ohm's law. Ohm's law says that V equals IR. This is Ohm's law. Much is said about this in your green sheets. Not that much, because I think it's empirical. It's just saying, hey, if you want to increase the current, you can increase the voltage, or for a given voltage, you could just reduce the resistance. So very simple. I'm going to just tap into Ohm's law. The voltage drop across R6 is V equals IR. So it's going to be I6 times R6. Calculator time. I6 is 1.30 amperes times R6. For me, R6 is 3.51. 3.51. That's capital letter omega. So we're going to figure out that current going through that resistor actually is going to cause a pressure difference. Just like water flowing through, like your garden hose. You're out watering your lawn, and if you kink the garden hose, you bend the garden hose, you're going to actually have a big old pressure difference that you created when you pinched your garden hose. And that's what's going on here. So I have 1.3 times 3.51 is 4.563. 4.563 volts. And just a discount double check, 1.3 times 3.51 is 4.563. All right, so let's write that down. Let's color code things. So 4.563 volts equals V6. Okay, and the value of R6, I already have it. I'm going to cut the clutter. That's it. That's my voltage drop across R6, because R6 represents you walking up to a garden hose, pinching it. And when you do that, you get that voltage difference, or that pressure difference. Let's see, for what's my voltage drop across 5? V across 5. My voltage drop across resistor 5. Ohm's law says V equals IR. So V equals IR generally becomes V5 equals I5 times R5. Let's go ahead and do 1.30 amps, because that's a series branch. R5 is in series with R6. Resistor 5 for me is 7.02. Omega, which is ohms, which is that resistance value. So if I take 1.3 times 7.02, I get 9.126 volts. 9.126 volts. And just a double check, what is 1.3 times 7.02? 9.126. Let's write that down. This is V5 equals 9.126 volts. So getting some good mileage out of Ohm's law. So now what's next? I'm going to find the voltage across R4. All right, so number 3, use this one right here. Use the loop rule. Use the loop rule. Use the loop rule to find the voltage across that resistor 4, V4. All right, so here's the loop rule. Loop rule means you got to draw a loop. So I'm going to draw a loop. Ready, set, go. There's my loop. So that's my loop. That's my loop. That red circle that's my loop. And you know what it says? The loop rule is basically a conservation of energy statement. So here's how I'm going to deal with that red loop I just drew. Well, before I get to that, there is a convention we have to talk about. By convention, and I've stated this before, but by convention, current always flows out of a battery's positive terminal. I'm going to change this color. All right, so I'm going to come back to that. But here's the convention. By convention, current always flows out of a battery's positive terminal. So like that. Okay, that's the convention. That's the battery's positive terminal. That's the current flowing out of the battery's positive terminal. Also by convention, for a resistor, what do I do for a resistor? For a resistor, current always flows into a resistor's positive terminal and exits the negative terminal. So I know that for R1, I know for sure this has to be positive and this has to be negative. And don't get confused. Resistors don't technically have a polarity, but when current flows through them, we do specify a positive side and a negative side. Let me say that again. Batteries have a polarity. There is an absolute positive terminal and an absolute negative terminal for the battery. That's the battery's polarity. A resistor is just a dumb device, but in terms of keeping track of what's going on with current flowing into a resistor and the voltage drop across a resistor, we always say current flows into a resistor's positive terminal and exits its negative terminal, which means over here, I can say this is a positive terminal. Got it. This is a negative terminal. Got it. This is the positive terminal for I5 or R5, I should say. Negative terminal. Okay. So back to the loop rule, which I'm going to change colors here. Okay, loop. This is my loop. I'm just going for a tour. I'm going to hire Probert. I'm going to hire Probert and say, hey, Probert, you need to go on a tour. You need to go around this loop. So Probert, you can start right here if you want. That's Probert. And Probert's going to go on a tour around this loop. So here's Probert's tour. Here's the record of Probert's tour. All right, Probert, you start there. You're going to have some voltage drop across R4. So Probert's, if I wanted to get like real up close and personal, Probert's basically going, okay, what's going on here? And then what's happening here? And then what's happening here? And then I've completed my journey. So once again, I'm drawing my loop like that just because I don't want to overlap things too crazily. But Probert literally is saying, what's the voltage associated with resistor 4? What's the voltage associated with resistor 5? And what's the voltage associated with resistor 6? And I want to keep a record of that. So V4 minus V5 minus V6 equals 0. Okay, so here's why I'm saying minus V5. When Probert is basically going through R5, this is Probert going through R5 right here. That's Probert's trip. Notice how Probert is starting at the higher voltage value and dropping down to the lower voltage value. So whatever the voltage is right here, whatever it is, it's less than it is here because that's positive. That's negative. This is positive because current goes into a positive terminal for a resistor. That's negative because current exits a resistor's negative terminal. That's why that gets counted as a negative. All right. And then it's the same exact story for R6. Probert goes through R6 during the loop here. And Probert's saying, once again, I have started at a higher voltage, whatever it is, I don't care. And I've ended up at this negative voltage, whatever it is, I don't care. I just know that my voltage has decreased. That's why that's a negative as well. And then as far as R4, I don't know. At this point, I don't know what's going on with R4. So the question is, should this be positive and that negative? Maybe, but I don't know, because maybe this is negative and that's positive. We have to figure it out. So the loop rule is conservation of energy. This is This is in the Hall of Fame. So here are your 8 inductees to the Circuit Analysis Hall of Fame. Loop rule is one of them. This is basically conservation of energy. It means for any loop, you can't destroy energy. You can't create energy. You can't destroy energy. Whatever energy you have has to, whatever gains, you know what this really means too. It means gains equals losses. So this is sounding familiar-ish to thermodynamics. Gains equals losses. That means whatever increases you have, whatever energy input, you have to use up all of those energy inputs. All right, so here's the loop rule, number 4. This is pretty easy. This is saying V4 equals V5 plus V6, or with numbers, V5 is 9.126 volts plus V6 is 4.563 volts. So I have my voltage drop across R4 because I'm going to use the loop rule. And the loop rule is saying, hey, I have a drop of 9.126 plus another drop of 4.563 equals 13.689. 13.689 volts. So you know what? I'm going to label that. I'm going to get rid of my loop just to clear the clutter. But that's the loop rule that Probert was hired to follow. And now my voltage drop, I'm using blue for voltage. So this is 13.689 volts. And now I have to worry about what's plus or minus. This has to be plus. This has to be plus. This has to be minus. How do I know that? Because I got a positive result is, I guess, one way of answering it. I got positive 13.689, not negative 13.689. So if I redo my loop again, loop rule, that forces my hand. That tells me for sure that this has to be a positive terminal, a positive side of my resistor, and this is the negative side of that resistor. And let's just do a sanity check because let's check with Probert. So Probert, let me get rid of this. Probert, you start right here, and you're going to start right here, and you're going to go from negative to positive. So when Probert does that, that's a gain. So if I'm following Probert, it's a little sidebar. Probert went from negative to positive. So that's a gain of 13.689 volts. Probert continues through R5. And notice Probert went from a positive value to a negative value. That's a drop. So Probert dropped some voltage. Probert's sensing a voltage drop of negative 9.126 volts. Probert then continues to finish the loop. It's another positive to negative. So once again, Probert starts at a high voltage and tumbles down to a lower voltage. So that gets counted as a negative or a voltage drop, negative 4.563 volts. And that equals 0 because once again, what goes in must come out. This is a gain. So I have a gain in voltage, and this is a loss or drop, drop, drop. And my gains need to equal the drops. So that's the loop rule. All right, so let me get rid of as much of this as possible just to keep the clutter under control. All right. So again, our goal is just to keep working from right to left. And I guess that's okay to leave all that stuff. All right. So you know what? I know about current. I know how to draw the current going through. I know how to draw the current going through R4 because of the convention. The convention says for a resistor, current flows into a positive terminal and out of a negative terminal. So I can use that. This is the direction of the current going through R4. it has to be down because current always enters a resistor's positive terminal, just like over here. It's the same for that resistor, and it was the same for this resistor, into the positive, exiting the negative, into the positive, exiting the negative. So there, I know the current. I know I4 is going down. Okay. What is the value of I4? We just got to keep fighting this battle, going from right to left. And in the process, you're going to learn just a giant amount of circuit analysis. So let's use Ohm's law. Ohm's law again says V equals IR. Generally speaking, V equals IR. I want to find out the current. So if V equals IR, I equals V over R. So specifically personalizing it for R4, the current going through R4 is going to equal V4, which I know, 13.689, over resistor 4's value, which I know. So V4 is 13.689 volts divided by the value of R4, which for me is 16.1 ohms. And when I do that, I'm going to have to store this in my calculator memory. 13.689 divided by 16.1. I get 0.85 and some change. 0.85 amperes. And I'm going to put this in memory location A. I'm going to need that for sure in my memory location. Store alpha A. And then let's write it down. Okay, so I4 equals 0.85 amperes. And I have that sitting there in calculator memory location A. That's it. So definitely taking advantage of conventions. And we did our first loop rule, and we've done Ohm's law. Now we're going to do junction rule. Okay, because here's my first junction. I'm just going to draw a junction right here. This intersection. A junction is where three or more wires meet, three or more wires, three or more devices. This is my first junction, and I'm going to give it a name. It's J1. J1 means junction one, just a labeling scheme. All right, so now, you know, one thing I know for sure the current going through R2 has to absolutely be in this direction. Why? Because of the junction rule. The junction rule, let me get rid of some of this stuff. The junction is another conservation law. So these conservation laws are great because they make things so easy. The loop rule is conservation of energy. The junction rule is conservation of charge. You can't destroy charges. You can separate charges, but you can never really destroy charges. So we're gonna use the junction rule. And once again, the way I like to write the junction rule is basically in equals out. Current going into a junction equals the current going out of a junction. So maybe even a little bit more sophisticated, and this is on your green sheets. If I sum up all of the current going into a junction, it equals the sum of the currents going out of that junction. In equals out. So what's going out of J1 right here? This is what's going out of J1. This current I know for sure is going to the right. This current I know for sure is going down because of this convention. So if this is going to the right and this is going to the left, I have no choice but to draw this current going into J1. That has to be the case because in equals out. And in the way, as far as junction one is concerned, junction one is saying, okay, this is in and this is out and this is out. So in must equal out. Conservation of charge is what the junction rule is basically saying. All right, so that means I can draw my terminals. This is going to be plus. This is going to be minus. And let's get a value. Let's get a value for I2, number 6, junction rule. Junction rule says in equals out. So what's going in? What's going into junction 1? Junction rule for J1. So for J1, junction 1, what's going in? I2, the current going through a resistor 2. What's coming out? I4 plus I5. So with numbers, I2 equals I4, which is, I'm just going to write this, that's a sitting there in my calculator memory location A, that 0.85, plus I5, which is 1.30 amperes. So the current going through R2, we're actually making pretty good progress, believe it or not, is 1.3, 2.15 and some change. 2.15 amperes and some change. I got to store that in calculator memory location B. Store alpha B. Okay. Definitely speak up when you see me make mistakes, because you can see, I mean, this is what we're all signed up for, you guys. We're engineers and scientists and tech people, STEM people. We love this amount of meticulousness, don't we? I do. I mean, it doesn't matter if I like it. It must be done. So let's get a voltage. Well, let's write that down. We're recording currents with orange. So I2 equals that 2.15 amperes. And for sure, that's living in calculator memory location B. 2.15 goes in, 0.85 and 1.3 come out. Let's get a voltage drop across R2. And that's a job for Ohm's law. So maybe picking up the pace just a wee bit. Okay. Number 7. Let's use Ohm's law to find the voltage drop across R2. In general, V equals IR, and personalized for R2, V2 equals I2 times R2. And with numbers, I2 is sitting in my calculator memory location B, and R2 for me is 2.43 ohms. 2.43 ohms. So I'm going to take calculator memory location B, multiply by 2.43, 5.22 and some change volts. 5.225 volts and some change. I gotta, because it's not a nice, it's a irrational number, I have to store it in calculator memory. Store alpha C, and let's write down my voltage, blue for voltage. So V2 equals 5.225 volts, and I have it in calculator memory location C. Okay. That's good. Loop rule. Let's do the loop rule to find R3. So hopefully you're kind of seeing the forest through the trees, the method to the madness. Loop rule. Here's the loop I'm going to refer to. Right, like this. There's another loop like that. Probert is going to go on this tour. So when Probert loops around that gray path, this is what Probert's going to be reporting. Probert says, okay, I'm encountering R3. There's something going on with the voltage across resistor 3 minus V2 minus V4 must equal 0. Because, just to repeat, this is saying what this is a gain. V3 is going to be counted as a gain. This is a drop. This is a drop. the total amount of gains must equal the total amount of drops because energy is conserved, as mentioned. So let's get a voltage value for R3. I'm just going to keep going with this algebra here. So this means voltage 3, the voltage across that resistor is going to equal V2 plus V4. This is why these pluses and minuses are critically important. So again, I make sure you ask if I need to provide any clarification. Why is that positive? Why is that negative? Why is this positive? Why is this negative? Because if you don't have that set up, then there's no getting past that. So I have V2, which is sitting there in calculator memory location C, plus, I should have wrote this as V4. This equals V4 plus V4, which was just 13.689. I didn't have that in my calculator memory, but now I have calculator memory location C plus 13.689 equals 18.9 and some change. 18.91 volts, and that's going to go into calculator memory location D. Store alpha D. And then let's write that down. Okay. We're getting ever closer to the EMF, which is our dollar sign. We're knocking on the door. This is V3 equals 18.91 for me, 18.91 volts, and that's sitting there in calculator memory location D. Okay. And I know that this has to be the positive, and I know this has to be the negative. And then, I mean, test yourself, make a mistake intentionally. Let's make a mistake. Let's call this mistakenly negative and positive, and it wouldn't work out because if I have this as negative and this is positive, if I go back and do the loop, I'm hiring Probert. Probert is going to say, well, this is a drop. This is negative 18.9. This is negative 5.225, and this is negative 13.68 and some change. So there's no way that can equal 0. So that's a good sanity check. All right, so that's how I know for sure that this is a positive terminal and that's a negative terminal. Let's go ahead and figure out the current going through that resistor. This is a job for Ohm's law, number 9. Ohm's law says generically V equals IR. And then if I want to find out the current, it's since V equals IR, I equals V over R, personalized for I3. I3 equals the voltage drop across resistor 3 over R3. And with numbers, I've got whatever is sitting there in calculator memory location D, my voltage drop, that 18.91 volts divided by R3. And for me, R3 is 2.43 ohms, 2.43 omega ohms. So I'm going to take my voltage across that resistor divided by 2.43, and I get 7.78 some change. 7.78 and some change amperes.
Can you scroll down a bit?
Yep. Amperes. And this is going to be memory. I don't know if I don't think I have to keep using these new memory locations, but I'm not sure. This is sitting here in memory location E. So I know the current going through resistor 3, which is taking me ever closer to my EMF, also known as the battery. Store alpha E. Okay, let's write that down. Let me zoom down. Okay, let's record that with orange. So I3 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 equals 7.78 amperes, which is sitting there in memory location E for me. There it is. Okay, and I know more aha moments. Aha. I know for sure this is the direction of the current from top to bottom. That has to be the case because by convention, current flows into a resistor's positive terminal and out of a resistor's negative terminal. So junction rule, we're so close now to the battery. The barbarians are at the gate. So this is J2. Junction 2. So it's junction rule time. What goes in must come out. Junction rule for J2. Junction rule for J2 says what goes in must come out. Well, I don't know what's going in, but I know what's coming out. Here's what's coming out. I2 and I3. I2 and I3 are coming out. I2 is going to the right. I3 is going straight down. So I now officially know, and I guess I've known it all along because I already had my resistor terminals specified. I know for sure this is the direction of I1. And I knew that because of that positive and negative term. But it's good to have this agreement going on. It's good to be in agreement like this, cross-checking. So what's going into J2, I1? I1, which is right here, is traveling into J2. I2 is coming out. I3 is coming out. And I guess I'm using orange. Let me erase that. So this is I1. I1, and I've known that all along. I1 is for sure going to the right. I2 is going to the right out of junction 2. I3 is going south or down, straight down out of junction 2. So junction rule says N equals out. I1 equals I2, which is sitting there in memory location B, plus I3, which is sitting there in memory location E, equals alpha B plus alpha E, 9.9 and some change. Okay. 9.93 amperes and some change, goes on. And I'm going to stick this in memory location F. Store alpha F. Okay. Let's write that down. 9.93. 9.93 amperes sitting there in memory location F. Let's get a voltage drop. I think we're 2 steps away. Let's use Ohm's law to find that voltage drop across R1. Ohm's law says generically V equals IR. And let's personalize that for R1. The voltage drop across R1 equals the current going through R1 times the R1 resistance itself. So for I1 is sitting there in my memory location F. R1 for me, R1 is 2.43 ohms, 2.43 ohms. So this is my voltage drop. F times 2.43, 24 and some change. 24.139 volts. This can go into G. I'm going to label that with blue. So this is V1. equals 24.139 and some change volts and sitting there in calculator memory location G. And then loop rule, one more loop rule. Here's the loop rule. Probert is hired to, I'm going to draw, my loop's going to look like this basically. So Probert's going to follow that loop, which means Probert's going to go from positive to negative. So that's going to be plus script E minus V1, because I'm going from positive to negative, minus V3, because again, I'm falling from positive to negative, and that's going to be my loop rule. All right, so let's tally that up. Number 12, loop rule, plus script E minus V1 minus V3 equals 0, which means that EMF equals V1 plus V3. V1 is sitting there in my calculator memory location G. V3 is sitting in memory location D. And if I do, oh, I almost didn't save that. G, E, F, G, store, alpha, G. Store alpha G. Okay. So alpha G plus alpha D is 43 and some change. 40 equals 43.053. I'm going to write down a bunch of these digits for a reason. 1118 volt. So that's it. That is a crazy amount of time. Not really. Let's be honest. I mean, it's not that much time. Plus, it was fun, but it's a lot of time. That's a lot of time spent. When you get practice, what I took an hour to do, however long, you'll be able to do this in 7 minutes, maybe 6, with practice. But this is the answer. This is the answer, and let's reflect. Let's take a moment and reflect on what we've just experienced. We have experienced a ton of conventions. You use the junction rule a bunch of times. You use the loop rule a bunch of times, Ohm's law, and that's kind of it. So we have really done 1, 2, 3, and 4. And we're back. We've survived. Maybe. Let's create this in falstad. Actually, we created this circuit before. In my case, I think I deleted it, which is not a big deal because I can just recreate it. But go back to falstad. We're gonna create this circuit in falstad, and we're gonna use we're all going to use my numbers and verify. We want to verify that the math and physics that we just did. We want to verify that all of this math and physics gave us a result that matches the simulation. And then obviously the next logical step would be to actually build this and confirm that physically we get an agreement. So that's the trifecta: math and physics agreeing with simulations, agreeing with actual physical experiment. So let's do the simulation part. And as mentioned, we had this circuit, but I deleted mine. Can I control Z it back? Nope, I can't. So I'm just going to recreate it. So we're all going to use my numbers, but for now, let's just do the basics. 1 resistor, 2 resistors, 3 resistors, and then we had that. Let me make sure I'm sharing what I think I'm sharing. I am. Okay, and then you got to find the node right there and find the node. And then here's my EMF, also known as my battery. And EMF stands for electromotive force, which is a device that actually creates, through some process, a voltage. Voltage source 2 terminal. There it is. And then let's connect wires. So you're going from node to node. And you can see charges are flowing. Done. So now we just have to set up the values. All right, so we're all going to use these values right here. Let's use, okay. All right, let's just do R1, R2, R3. 1, 2, and 3 all equal 2.43. 1, 2, and 3 are all 2.43 ohms. So 2.43. Yes. 2.43. Yes. And 2.43. 2.43. All right. And it's showing as 2.4, but it's showing 2.4, but it's recording 2.43. And if you want to just verify that, put your cursor over any one of these resistors, and it's labeled 2.4, but it's just you can see in that pop-up data box, it's 2.43. 2.43 for these three leftmost resistors. Yes. All right. My middle vertical resistor has a value of my middle vertical resistor is R4. R4 is 16.1. So R4 is 16.1. Let's set that 16.1 ohms. Got it. R4, which is the middle vertical resistor, is 16.1. R6, which is that rightmost vertical resistor, the rightmost vertical resistor, which is R6, is 3.51. 3.51. 3.51. Last but not least, that third horizontal resistor is not 1K. That third horizontal resistor is R5, and R5 is 7.02. 7.02. 7.02 there. Okay. So, and again, chat amongst yourselves in the chat box or unmute your mic and interrupt me. Let's enter the battery voltage. And this is why I wrote down all of those digits of precision, because I just because I can. So, because I want to be precise. Double click on your EMF, also known as the battery. Notice how the positive charges, and I can slow things down. What if I slow down my current speed? Notice how those positive charges are flowing out of the positive terminal, and they flow into a resistor's positive terminal, but out of a battery's positive terminal. Double click on your battery, and let's change this. Ready? 43.05331118. Let's type in, let's drag along all those digits. I'm just looking at my calculator. My calculator says 43.05331118. Okay, and then say okay. That's it. So we have all of the voltage values set. We have the voltage value set. We have the resistances set. Let me know if I need to repeat anything or if you can't see something. Because again, this is showing 2.4, but in reality, it's 2.43. So now the whole crux of this problem is you need to design a circuit and provide whatever battery voltage was needed to get 1.6 amperes flowing through R6. That was the problem. This problem gave us, it said I6, which is flowing through R6, is actually known to be or needs to be 1.30 amperes. So let's verify that. Falstad. If I put my cursor on R6, you can see that my data window pops up, my data box pops up, and it says the resistance or the current is 1.3. So that's verification. That is some verification right there. You have designed a circuit, and specified a battery voltage that produces that 1.3 amperes. So we could check some other stuff too. We don't have to check everything, but I'm looking at R3. look at R3, which is that leftmost vertical resistor. We did the math and physics to say that the voltage drop across R3 is 18.91 volts and some change. Let's go to falstad to see if we get 18.91 volts across R3. Here's falstad, here's R3. If I put my cursor on R3, it says 18.914, which is actually even more precision than I was blurting out. So no matter where you go, you should be getting confirmation, and you should be aware of the directions too. Look at, I have, this is my current flowing out of junction 2, flowing out of junction 2, flowing into junction 2. So we should have complete agreement between what you see here in the simulation with all of this math and physics. And we do. So as far as what you need to submit right now, get out of construction mode, hit escape. Let's go into just selection mode. Take your circuit, drag it over here, and then put your, it's a little bit too far. I cut off my resistor. All right, so there. Put your cursor on that 3.5, that rightmost vertical resistor, which is R6. And now let's take a snip of that. Window Shift S. So I need to take just the pertinent screen real estate. I don't need all of the other junk. And your numbers, we should all have the same exact numbers. 1.3, 4.563, that rings a bell. We did calculate that. 3.51 ohms, 5.932 watts. All right, so there's your screen snip. Let's go to a Word document. Word document. And I guess I can reuse. All right, so here's a brand new Word document. Right here. Let's do a paste. So there's your paste. And then, you know what, a better way to do the header is this. Just do a 3-column table. So above your paste, just say insert table, and let's just do a 3x1 table. Ready there. And this is, this was your name. This was physics 212 dash. I gotta remember the syntax. I have to be aware of the syntax. All right, so here I'm gonna reclaim this for a second. All right, so let me do that snip again, because I was forgetting the header syntax, and I have to be consistent, because again, I need to hand this off to other people. Right there. All right. We all agree with those numbers. There's my snip. Back to Word. Oh, sorry. I was here. I just re-snipped my falstad circuit, and now I'm going back to Word. And what I was saying before is it might be better just to use a table. So I'm going to clear this out and say, let's just insert a table. Okay. All right. Insert table 3x1. All right. So what was the, having said that, I just literally deleted it again. This was, what you guys help me out here. This was, I think, name. What was this? That was the right side. This was the middle. Physics 212-4. 14. And I think this was, oh yeah, I do remember. This is chapter 27 quiz, falstad. I do remember 27.33. Ignore that. And then I'm going to do center justify. And that's good for your header. So it's you don't write Chris Wood. This is your name, not my name. So that's what you can submit. Save this Word document with that header, save it to a document, and then go into Blackboard. And if you go into Blackboard, you should see Physics 212 course documents. And you should see chapter 27 quiz, falstad 2733 right here. So there's the Blackboard area where you need to submit the document you just saved. This is what the document looks like. Again, don't type in my name, type in your name. So this would be your name here. Okay.
Are we using our data or yours? It'd be ours, right?
I mean, my data. Everyone uses my data. All right, so that goes there.
What was again, the battery voltage? I didn't get that one.
We'll go back. I think I literally just deleted it by mistake. Oh, well, the battery voltage was this. I'll just put it in the notes. For your battery voltage, battery voltage was 43.05331118. That was the battery voltage. That was the EMF.
Okay, thank you.
Yep. So you guys can finish that up while I get, that was quiz one. No quiz will be nearly as long as this, but that was a great quiz and a great simulation. Great indeed. 27 quiz 2 is next. Give me a minute. You guys might need another minute anyway. Quiz 2 coming up. I'll start mentioning this now, but you will need to use Excel on the exam, and you will need to use falstad on the exam. So exam 3 will be a little bit different because it will be required to use a spreadsheet, and it has to be Excel. So for those of you using Google Sheets or something else, just make sure you get yourself some track record with Microsoft Excel, because that's what you're going to have to use for exam 3, because that's what's available to us in the lab. All right, so this is quiz 2. It's now 9:57. Okay. At this point, you guys, for those of you who, again, and I hope it's everyone, but for those of you really dedicating yourself to the traffic light report for extra credit, honest extra credit, and just keeping yourself up to speed. This is, to me, that what you just did constitutes red. You just basically turned chapter 27, problem 33. So right here, you could all right now, for those of you who finished this and got the right answer, you get to put the number 1 in chapter 27 homework, problem 33. Even though maybe you didn't do the homework yet, but to me that constitutes red because you got the right answer. And just remember this: getting the right answer is just the start of the process. Don't let yourself think, I got the right answer, I'm ready for the exam. No, that doesn't usually happen. All right, so there. That hopefully is buying you some time if you need it. And we can go to chapter 27, quiz 2, which I'm thinking looks like this. Chapter 27, quiz 2. I hope it's looking like that. Let me know if it's not. Okay. Let's now actually talk about circuit reduction. Okay. Circuit reduction. So you have been hopefully nicely exposed to some conventions, the junction rule, the loop rule, Ohm's law. Let's now focus here on circuit reduction, and we're going to have series and parallel resistors. All right. So here's the bottom line. I need to figure out, this is my dollar sign right there. That's my dollar sign. What's the current going through R2? And then this is my other dollar sign. What's the power? Okay, so I have two dollar signs. Let's do reduction. All right. Well, I can see, let's talk about junctions. So I'm going to draw, this is a junction right here. Right. I'll make it like large like that. This is actually a junction because a junction is where three or more wires meet. And R2, these three resistors, well, yeah, these three resistors and that battery, they are all connecting together at that junction. And you might say, hey, Chris, not so fast. You might say that, well, really, here's a junction and here's a junction. So this is another kind of convention. You're right. I do have two junctions, but because there's nothing between those junctions, I can collapse them into a single junction. You don't have to, but I'm just saying you can. This junction and this junction can be collapsed into a single junction like this. Okay, so I'm just going to consider this blob to be a junction. The combination of those two other junctions, those are equivalent. Same here. You would say you have a junction here and a junction here. And I would say that's true. And I can collapse those as well because there's nothing between them. So there, I have those two junctions. If I wanted to label things, this would be junction 1 and this could be junction 2. And I don't have any other junctions. I just have those two junctions. So I'm doing that. You know what? When I do that, I could say, aha, R2, and R2 are in parallel. Because remember the sanity check for parallel. Parallel means devices are in parallel if they share the same junction on one side with no intermediate devices, and they share the same junction on the other side with no intermediate devices. These three resistors satisfy that criteria. This R2 and this R2 and this R2 are all in parallel. So this is kind of like the flip side of capacitors. If these are in parallel, here's the equivalent. Here is the equivalent resistance. For resistors in parallel, it looks like capacitors in series in terms of the form. It's 1 over this resistor plus 1 over this resistor plus 1 over this resistor. So let's get a number on that. For me, it's going to be 1 over R2 is 13.7. 13.7 ohms plus 1 over 13.7 ohms plus 1 over 13.7 ohms. So if I do that on my calculator, here's that equivalent resistance. It is 4.5 and some change equals 4.566, repeating in some change. Let me just do this. Okay. Good. All right. So now I'm going to redraw the circuit, number 3. Update. So this whole thing we're doing is circuit reduction, redraw. I'm reducing this circuit. Redraw the circuit. So I have, here's my battery. Here's R1. And now all 3 of these R2s are going to collapse into an equivalent. I'll just put them maybe right here. So this is what I'm left with. This is EMF. And they did indicate that, yes, this is a positive terminal. That's a negative terminal. This is R1. And this is REQ. REQ. Maybe I'll put RE. You know what I'm going to do? I'm just going to put R222, R222. And I'm going to change this because I do like this convention. It's just nothing official, just how I happen to keep track of stuff. So if I'm collapsing 3 R2s, this is just why I'm going to call this R222, not the 222 ohm resistor, but what you see is hopefully explanatory enough. All right, so you know what? This is series. Aha. Series. These are now in series, not in parallel. So I'm going to have R1, 222. If they're in series, it's going to equal R1. So what I'm writing down for the equivalent resistance for resistors in series kind of looks like what we did for capacitors in parallel. So there's that sort of like dichotomy, plus R222. R1 is 4.56. 4.56 plus R222 is 4.566 repeating. So if I add those together, plus 4.56, I get 9.1266 repeating ohms. I better store that. Store alpha A. So we can answer. Well, we can answer part B right now because this is what my circuit looks like after this reduction. Number 4, number 5. I have this. I have my battery and I have a single resistor. This battery is EMF, is an EMF. This is R1222, and I have a value for that. That's sitting there in memory location A. And just some recap of a convention. By convention, current flows out of a battery's positive terminal. So current's flowing out, going this way, going around, and going through R2 1222. Anyway, let's get let me say this again. The current coming out of a battery is referred to as circuit current. I sub C is circuit current. It's the current coming out of a battery that's fed into whatever's connected to it. Okay. So Ohm's law to the rescue. Number 5, number 6. 6. Ohm's law says that V equals IR, generically speaking, and specific, well, if V equals IR, then I equals V over R. And specifically in our case, V refers to the voltage, and we just have one voltage source. It's the EMF. It's the EMF voltage all over that equivalent resistance. So with numbers, my battery voltage is 11.9 volts. all over memory location A in terms of the resistance. So this is my current divided by 11.9, 1.3 and some change. 1.303 amperes. Let's put that in memory location B. And now there's something new. Now, actually, it should kind of make the list. Maybe I should actually call this power. Really, that you could argue that should be a number 9. Because part B says how much energy is dissipated by all 4 resistors in 2.65 minutes. So we're doing part B before part A. All right, so P stands for power. Power is the rate of doing work. So it's the amount of work per time that gets done. There's a difference between power and energy. Power is the rate of energy consumption or energy production. In the case of this, power is the rate at which these resistors are burning up all of that energy. Because if you just look at this combined resistor down here, let me clear it a little bit. These resistors are collectively doing one thing. They're producing heat. So this equivalent resistance, all these resistors produce heat. That's what they do. They produce heat. That's a form of work. These resistors are doing the work to produce. Sometimes you want resistors to produce heat. Sometimes you don't. When you boil a pot of water on the stove, you want resistors to produce heat. Most times or oftentimes you want to reduce the amount of heat production because that can be wasted energy. So in this case, how much work is done to produce all of this heat? And technically, I have these alternatives. So this was derived for you in the green sheets. I'm not going to rederive it here, but I will say this. I do remember that, let's see, power is the rate of doing work. And I remember the relationship between work and potential energy is this. And I do remember potential energy is equal to Q delta V. So negative Q delta V over time. And Q over time is current. So here's how you get one of these. And then how do you, so I literally just derived this expression like right here, I delta V. How do you go from here to here? Ohm's law. How do you go from here to here? Ohm's law. So anyway, I'm taking 10 seconds to go what you should go through much more methodically, but those are our expressions for power, electrical power production or electrical power consumption. The battery produces energy, the resistors consume energy. They're saying how much energy is dissipated by all 4 resistors in 2.65 minutes with my numbers. So you could say, well, number 8. I know that power equals, I'm going to write power is work over time, or alternatively, energy per time. Those are equivalent statements. So I wrote down, and I'm standing by it. Power is the rate of producing work. But they said, I'm not interested in the work done by the battery. I'm interested in the energy dissipated by the resistors. So that's how I'm saying these are equivalent. Work and energy. Work is just energy put to use. So if that's true, I can say energy equals power times time. Okay, and I have an expression for power. I guess I could do, let's do I squared R. Let's do I squared R. That's a common term. A lot of times you hear the expression I squared, like I squared R. I mean, I'm spelling it phonetically, but a lot of times you say, hey, what's the I squared R power? So this is a common expression, actually. So with numbers, I have whatever is sitting there in calculator memory location B. Oh, wait, I forgot one thing. Times time. I forgot that times time. All right, so now again, with numbers, I squared is memory location B. R is the equivalent resistance, which is sitting there in memory location A. Time is 2.65 minutes, 2.65 minutes. And I know that's not going to be dimensionally correct, so I need to convert. And I forgot to square it. This is I squared R times time, and time is 2.65 minutes times 60 seconds over a minute. Okay. I squared R. So again, there's I squared R, there's time, and converted from minutes to seconds. Okay. I squared times R alpha A times 2.65 times 60. 2467. Okay, so that's the power. 2467.05 watts. I'll let you do the dimensional. Well, maybe I should do the. All right, so this is anyway. This is the energy. This is the energy dissipated in the form of heat by those 1, 2, 3, 4 resistors. That's the answer to part B. I will do the dimensional analysis just because it's got to happen. Let's see this expression right here. I'm ending up with that. So I squared is amperes squared times ohms times, I convert from minutes to seconds. Does that give you watts? Well, actually, I'm going to sidestep that. I'll let you guys do the dimensional analysis because that's going to take too much backtracking. But anyway, I guess that's the question. I'm going to like kind of weasel out of my commitment and say, you do the dimensional analysis. Okay. Which means you're going to have to go back to some basic definitions. All right. So that's part B. Part A says, what is this? What is this current? So now this is where we start to backtrack. All right. So, well, you know what? Speaking of taking the cowardly way out, I think I'll do it like this. We could take an approach kind of similar to what I did here, which was some heavy lifting, but I guess we can take advantage of some simplicities here. Look at my current. Let me redraw. Let me erase this right here. No, there's not much to erase. I'm going to leave everything intact. Here's my current. I know my circuit current. Ready? By convention, current always comes out of a battery's positive terminal. So here's the current coming out of the battery's positive terminal. And it's going into this junction. So this is my circuit current. I have this sitting here literally in memory location B. That's the current going into this junction. And you can see, so this is like the easy simplified way versus the very heavy lifting way, because I can see I have two resistors. I have three resistors. I have three equivalent resistors. If you're the current going into junction J1, you're going to be split three ways evenly because R2 is the same everywhere. This resistor right here is the same as this resistor, is the same as this resistor. You're going to branch off into three equivalent paths. So this could be one of your pathways. This would be another pathway, I2, and then this would be the third pathway, I3. And I'm just saying in the name of expediency, and it's good to see the simplifications because these three resistors all have the same value. They're going to draw current at the same rate. So I'm going to say I1 equals I2 equals I3. They're all the same currents. So let's take that circuit current whatever is living there in calculator memory location B, which I figured out right here. Let's divide that by 3. Because 1/3 of it goes through each of those resistors. So I'm going to take calculator memory location, and I guess I just erased it. I never did start. So 11.9 divided by alpha A, that looks good, divided by 3 is 0.434 and some change. So that's how you get the answer to B. So again, a little bit of taking the easy way out. Not that there's anything wrong with that, but this is what I'm calling, well, the current that corresponds to I1 is I1 equals B over 3 or 0.434 for me, 0.434 on and on and on amperes. And this is the answer to part A right here. Oh, wait a minute. Okay. This is the answer to part A, taking advantage of some simplifications that I basically talked my way and commented my way through. Okay. So we can check off. We got to look at series and parallel resistors. Okay. And we did power. So of these 9 items, you guys got to first look at 7 out of those 9. So let's do another quiz. Quiz 3. Let me just take a quick look. Quiz 3. Okay. Quiz 3. I think this might be the last thing we do today. Could be, because this will take some time. The next quiz. Chapter 27, quiz 3. Okay. Chapter 27, quiz 3 should now be available to you. It should look like this. This is a brand new introduction to something new. Let me get rid of this old content. And this is we're going to learn the mesh method. And exam 3 is the only exam where you can actually anticipate a problem type. Mesh method will absolutely be part of exam 3. So you don't have to guess. You don't have to worry, should I, do I really need to learn this? Or, the answer is, of course, you need to do the traffic light report on everything. But this is the mesh method. This will be for sure on exam 3, which means you for sure will be using a spreadsheet, and you will for sure be using falstad. So it's nice. It's nice to have that amount of certainty, that degree of certainty. There's no guesswork. And then as far as other problem types, I just sort of combine capacitors and resistors into other problem types. Anyway, you'll see everything, or you should assume you're going to see everything. This is homework problem, chapter 27, problem 35. And we're going to take this as an opportunity to learn the mesh method. Let me get, this was our Hall of Fame right here. Take a copy of it. All right, this is mesh method. And I should add a number 9, power. Okay, so that's better. All right, so we're gonna take this opportunity to use the mesh method, which is a linear algebra type of thing. All right, so okay, here goes. And this, let me show you what this is. There's an exam problem, for loop mesh. Okay, I think this was an old exam. For you'll probably have a 5 loop mesh, but this is what you're going to do in on exam 3. And I'm tempted to maybe actually just start with this. Well, okay, maybe not. But anyway, this is what the exam problem will look like. It will be a different circuit, but this is, I think, exactly what you'll have to cough up in terms of what you see here in this box. All right, so let's do chapter 27, quiz 3, and learn the mesh method all at the same time. This is all in your green sheet. So everything I'm talking about here is summarized in the green sheets. Okay, so let's create a loop current. Let's create loops. All right, so in your notebook, you should be taking, and colors help, ready, set, go, like that. So instead of drawing like that, I don't want to overlap things. I'm just going to say this is loop current 1, loop current 2, loop current 3. So this is definitely going to tap into this. I mean, the good thing about the mesh method is it's actually pretty darn impressive, number one, what you're going to be able to do. But this is going to tap into Ohm's law and loop rule. In fact, that's all it's going to do. All you're going to do is apply Ohm's law and the loop rule as many times as you need to get everything covered. So there's a lot of procedure that's going to happen, but the mesh method is nothing more than Ohm's law and the loop rule. So step number 1, identify the loops. All right, so this is in your green sheets. I'm just going to kind of paraphrase here. ID the loops, ID loops. And sort of the rule is every element needs to be covered by one or more loops. So ask yourself, is R2, is this resistor covered by a loop? Yeah, it's covered by I1, and you could say it's covered by I2. So as long as it's covered by at least one loop current, then that's good to go. So let's do a checklist here. R2 is covered by at least one loop. Look at R1 over here. R1 is covered by a loop, not 2 loops, but 1 loop. So that's fine. Let's look at this bridge. This is like a bridge resistor because it looks like a bridge between points B and C. Is that covered by at least 1 loop? Yeah, it is. In fact, it's covered by 2 loops. R3 is good to go. What about R2? Yep, covered. What about my battery? Yes, covered. What about R1? All right. So anyway, I've covered all of these circuit elements with at least 1 loop. And then the other caveat here, the way it works out in terms of keeping track of things, no loop can be contained by another loop. No loop can be contained by another loop. Okay, and I've satisfied. And here's an example of me violating that rule. If I drew another loop, what if I just drew a loop like this? And sometimes you might want to draw funny looking loops like that. But if I call this loop 4, no, because loop 4 completely contains one or more other loops. And that would cause a conflict in how we're going to crunch numbers. So, all right, I've got 3 loops. And just to keep things simple and pristine and easy to deal with, let's always draw loops. All loops are counterclockwise, or I'm sorry, clockwise, CW, clockwise. You could draw them counterclockwise or clockwise, and it doesn't matter. But I'm just saying for simplicity, especially for the learning process here, let's draw all of these loops clockwise. So we're done. This is actually a big step. I am done with my 3 loops, and I needed a minimum of 3 to cover each circuit element at least once. Okay. If you wanted to, I guess I'm seeing an alternative. I could actually say, well, here's another loop like this, and this is another loop, and that's completely valid. So I guess, you know what? I guess we could actually get away with drawing only 2 loops, but you know what? This is our commitment. It's the same either way, and it's probably the same amount of work either way. But anyway, all right. So the loops are done. Ready for the next step? Let's do the loop rule. Loop rule. Okay. So for loop one, I'm going to turn on my graph. The loop rule is conservation of energy. Whatever gains exist in the loop has to be offset by an equivalent amount of losses. So let's do the loop rule. So Probert, let's hire Probert. Probert, loop 1. So here's Probert's journey. Probert goes from low voltage to high voltage. Probert is following this loop. Probert goes across R2 and then across R1 and then done. So I'm drawing loop 1 like this. I drew loop 1 like this just because I didn't want to clutter up the screen too much. But loop 1 means when you hire Probert, let me just repeat it. Probert, and you can start anywhere. You could start anywhere. I'm just going to start it doesn't matter where I start, but I'm going to start anywhere. There's a voltage gain. This is going to be a voltage loss. This is going to be a voltage loss. And the gains equals the losses, and that's my loop. So one thing I better do is my resistor terminals. We talked about this a lot. I talked about this a lot in the last problem. This has to be a positive terminal. Positive, negative. From the perspective of I1 is going into a resistor's positive terminal and exits the resistor's negative terminal. So again, this is from the perspective of I1. Now, I am going to add it here. I1 is actually going through R1 as well. So I'm just going to modify it. This is loop 1. I didn't modify. I'm just like drawing it to look like it's going through, to make sure you guys realize it's going through each of these elements. So this needs a positive. From the perspective of I1, that's a positive. From the perspective of I1, that's a negative. Let's talk about the perspective of loop current 2. From the perspective of loop current 2, this is the positive. Change colors. This is the positive from the perspective of loop current 2. This is negative. From the perspective of loop current 3, this is positive and this is negative. And let me maybe just this time draw these loop currents to be maybe a little more tighter fitting loop currents, just to make sure all confusion is avoided. This is loop current 2. It has to go clockwise. So loop current 2 is going through R2, R1, R3. All right, there. So not as abstract, but maybe more intuitive. Loop current 3 is going through R1, going through R3, going through R2, and then coming back home. Okay, so there. All right, so now, again, we're talking about loop 1. And all this is loop rule and Ohm's law. Here's loop 1. All right, plus E, plus EMF. Probert climbs the mountain. I always think of it like climbing a mountain. This is base camp. So this is low gravitational potential energy, and then this is high gravitational potential energy. Anyway, this is how I think about it. I think of Probert as having to climb up a mountain. Probert climbs up this mountain. Probert goes from low voltage to high voltage. So that's a gain. So that's why I'm writing That's why this is written as a plus. That's a positive. That's a voltage gain or voltage rise. So let's follow Probert's journey and keep track of it using Ohm's law and the loop rule. All right. All right. So Probert is encountering R2. Probert's encountering R2, and two things are happening at once. Probert is experiencing a voltage drop due to loop current 1. And at the same time, Probert is experiencing a voltage rise due to loop current I2. Because check it out. Here's Probert going through R2. It's going from a positive to a negative from the perspective of I1, but it's going from a negative to a positive from the perspective of loop current 2. So let's do this. All right, here's Ohm's law. Ready? Minus I1 R2 plus I2 R2. Done. I'm done with this circuit element. And let me double check that. I1, this is loop, this is I1. So if I wanted to, I could maybe even name this. This is technically I1. And this is technically I2. Let me do that. And this is technically I3. Okay. So Probert is traveling through R2, experiencing a voltage drop because of I1. Got it. And at the same time, I'm going from negative to positive. So that's a rise. So basically, I1, the current I1 going through R2 is being offset. Let me say it like this, saying the same thing, but maybe in a different way. Here's the loop current. Loop current I1 is literally going through R2 in that direction, the way I'm drawing it. So that's loop current I1, and loop current I2 is offsetting. So these two currents offset each other, and that's I2. So that's why and you can see here, they're offsetting. All right. So let me back off on that just so it's not too cluttered. And that is thanks to Ohm's law. I figured that out. And you know what? Probert continues through R1. So here's R1. Ready, set, go. Minus I1 R1 plus I3 R1 equals 0. Done. Let's talk about Probert going through R1. All right, Probert starts here and goes through that resistor as I'm drawing here. And from the perspective of I1, look what's going on. I1 is producing a drop. That's why this is negative. I3 simultaneously, I3 is going in this direction. Let me just draw a zoomed in version of, here's I3. I3 is going in that direction. And because I3 is going in that direction, that gets a positive, that gets a negative, and I3 is, as I1 is going through R1, it's a drop due to current 1, but a rise because I'm going from, Probert's going from negative to positive from the perspective of I3. From the perspective of I1, Probert is going from positive to negative. So that's why this is a positive. And I'm done with loop 1. Look at that. And this sounds crazy at first, but you'd be surprised how you'll ramp up with this pretty quickly. I mean, not without effort. It's going to take effort, but it's still going to go quickly once you start investing in it. All we did is Ohm's law and loop rule, and to be honest, a bunch of conventions and some rules, but not an infinite number of rules. And some rules. I think a reasonable amount of rules. We got to keep track of how we produce these equations. Let's do loop 2. And if we want to keep track of things so we can crunch them later, we have to kind of be consistent. Loop 2. Okay, if I just look at loop 2, Probert, I've hired Probert. Probert, you can start here. You can go through R2, then you can go through R1, then you can go through R3. So Probert's going to do all of that as indicated. And so let's tally up Ohm's law. All right, so it's going to be minus I2 R2 plus I1 R2 minus I2 R1 minus I2 R3 plus I3 R3 equals 0. So I know it sounds crazy. Let's go through this. I did that. The amount of time it took me to do that is the amount of time it will take you to do that in short order. All right, so I just want to make sure I'm right though. Probert is going to go through, is going to go clockwise through R2, then through R1, continuing clockwise through R3. So, yep, I think that's correct. Just being paranoid. So now let's talk about loop 2. This is loop 2. We're on loop 2. So loop 2, I'm going from loop 2. Well, I'm going from loop 2 is going from positive to negative. So that's a drop. That's why this is a drop. And this is Ohm's law. I should maybe stress this more. This is nothing more than Ohm's law. This is Ohm's law. And you know what? This is Ohm's law, and this is Ohm's law. Same here. I should have made that maybe more obvious. But this is what I'm saying. This is nothing more than Ohm's law over and over again within a loop. So this whole thing right here, this is a loop. And I just got Ohm's law a bunch of time and a battery voltage. Same down here. This is loop 2. And loop 2 is just comprised of whatever batteries or whatever EMFs I have and whatever Ohm's law voltages I have. Okay, so let me get rid of those just to avoid clutter. It's just Ohm's law applied around the loops that we specify. All right, so I'm looking, loop 2 is, here's loop 2. Loop 2 is, I'm going from positive to negative. So if I use Ohm's law, what's that voltage drop? V equals IR. So that's why I have positive to a negative. That's why that's negative, because it's a drop from positive to negative. And this is why it's IR, because for the umpteenth time, Ohm's law is V equals IR. This is voltage. For what we're doing now, this is voltage drop or rise across a resistor. Okay. All right, so let's keep going. But at the same time, I2 is going from positive to negative. I1 is going from, let me say it again. The same time, I2 is going from a positive to negative. It's also going from, I1 is going from a negative to a positive. So that's why this is considered a rise. And let me say that. So I2 is a drop, but it's being offset by I1 because I1 is going in this direction because everything's clockwise. So this is I1. I1, this is I2. And you can see I'm drawing it right there, very up close. I2 is going from positive to negative. So that's a drop. But over here, I have this negative to a positive. So that's why this is counted as a rise. So this is a drop. And this is a rise. And then what I always think of them, they offset. I2 and I1. I2 and I1 offset each other. That's why that's negative. That's positive. Okay, so let's just finish this. Done with that resistor. Okay, and then let me keep the clutter to a minimum. All right, so Probert now encounters R1. So Probert, we're keeping Probert done with that. Probert encounters R1. And because there's only one current, and in reality, there are simultaneous currents going through a wire, but because there's only one current going through R1, it's that I2, current 2. This is going to be positive. That's going to be negative because by convention, I2 must go into a resistor's positive terminal and exit its negative terminal. Okay, so that explains why I have a drop. That explains why this is negative and this is Ohm's law. What's the voltage drop across here? It's whatever Ohm's law says it is. V equals IR. So that's why that's negative I2R1. Okay. Last but not least, Probert now is completing the journey going through R3, and Probert is going to record a drop due to I2, because notice I2 is going in this direction. This is I2, and it's being offset by I3 going in this direction. That's why this is my voltage drop across R3, and this is a voltage rise because I3 is going in the opposite direction compared to I2, and that's why it equals 0. Let's do loop 3 and then tally everything up. Loop 3. Okay, clear the clutter. Loop 3. Okay, there's loop 3. Probert is making this journey, always clockwise like that. So Probert first encounters resistor 1. So when Probert encounters resistor 1, that's going to be a voltage drop. Ready? Minus I3 R1. But at the same time, I3 is going through R1. I1 is going in the opposite direction. You get that offsetting effect, plus I1 R1. Done with R1, and now we're on R3 during our journey. Probert says, well, I3 is producing a voltage drop, I3 R3, Ohm's law, V equals IR, but that's being offset by I2 R3. And then last but not least, Probert encounters R2. So Probert just is going to notice a drop minus I3 R2, and we're done, equals 0. And this should be and we'll talk about this. This should be a positive terminal and a negative terminal. Okay. And let me just double check that. Okay. Probert starts. I'm going to start Probert. I just want to be super paranoid. Probert starts here, is going to deal with R1, and then deal with R3, and deal with R2. So to keep track of all of those rises and drops, I am saying Probert encounters R1, so that's a drop, because plus to minus, it's plus to minus here, but it's minus to plus here. So from I3, you can see I3 is going from plus to minus, but simultaneous to that, I1 is going from minus to plus. All right, so you have that offsetting effect. All right, so that's why done with R1. Then I encounter R3. Here's my drop being offset by I2 going in the other direction. And then last but not least, R2, that's my drop, and there's nothing offsetting it there. There you go. In many ways done. Well, done with the setup. So now all we have to do is spend literally probably 2 hours crunching these numbers, because you know all of these values. You know the value of all the resistors. All the resistors are known. I know R1, I know R2, I know R3. I know the battery voltage. This battery voltage is known. Got that. So then if we spent, I don't know, an hour, or if we spent a really long amount of time, we would be able to find we would be able to find I1, I2, and I3. And you would say, of course, Chris, because you basically have three unknowns and three equations. Remember that from algebra? You have three equations, the loop 1, loop 2, loop 3 equations. And across these three unknown equations, you have three unknowns. So what happens though, like exam 3 is here, and this is a 3-loop circuit. You're going to have a 5-loop circuit. That would take you the better part of a morning to figure that out if you had to do that. So we're going to use a spreadsheet to do the dirty work for us. All right, so get into your spreadsheet. I will get into my spreadsheet. Here is a spreadsheet. All right, and then the spreadsheet that you're creating now, you can actually keep, because, and you can, not only can you keep it, not only should you keep it, you can reuse it on exam 1. So you have motivation to put together a pretty comprehensive spreadsheet. So let's start creating the spreadsheet. All right, I have 3 resistors. Okay. Oh, I have a bunch of resistors. Okay, so anyway, R1, R2, so you can follow along, R3. And then I have a battery like that. So let me make it easy, make sure you guys can read this easily. I'm going to highlight every cell in the spreadsheet and change to Cambria font. Not Cambria Math, but just Cambria font. All right, so you can use, let's do this, you guys. Let's, I don't know if I should, I guess use your numbers. Use your numbers. Actually, I got a better idea. Let's all use my numbers. And then when it comes time to answering your question correctly, you just make a simple change. So let's all use my numbers, and then you'll switch to your numbers when we're done with everything. All right. So my numbers, just so we can get verification. R1 is 1320, R2 is 2520, and 3060. So R1 is 1320. R1 is 1320. R2, according to my numbers, 2520. So let's all use my numbers, 2520. And R3 is 3060. 3060. And that battery voltage is, my numbers again, 10.2 volts. 10.2. So use these numbers, and let's just do some justification. Let's do middle center. All right, like that. All right. And again, this spreadsheet that you're making, you should kind of repurpose it for use on subsequent homework problems and quizzes and exams. And I want to just check my numbers here. R1 is 1320. Yes, 1320. R2 is 2520. Yes. R3 is 3060. Yes. Battery EMF. I have to stop saying battery. EMF is 10.2. That looks good. Okay, so now let's do the spreadsheet. All we're going to do is we're going to organize these equations into a nice, consistent approach. I have 3 loop circuits. I have loop I1, loop I2, loop I3, and then I'm going to have the voltages for each of those loops, which I'll just call V. Okay, so then loop 1, and then loop 2, loop 3. Don't go crazy on the formatting. You can go crazy on the formatting later, but don't let it make you fall behind. Don't fall behind just because of formatting issues. Just capture the key content at this point. Okay, so now here's the heavy lifting. I'm going to take, actually I can do this, I think. I'm going to take all of my Ohm's law. I'm going to take all of my effort right here, and I'm going to put this into my spreadsheet. So let me take a snip, go to my spreadsheet. All right, so this is what I got to put into my spreadsheet. Okay, let me get rid of some of this. All right, here goes. Loop one. I have loop one here. All right, so I have negative I1 times R2 ready right here. Well, let me cluster some things first. All right, so for I1, all right, I1 equals, check out the coefficients of I1. If I look at loop one, well, there's an I1, and I have I1 multiplied by negative R2. So negative, and then click on R2, click. But then I have another R1, I'm sorry, I have another I1 over here, and that's being multiplied by a negative R1. So minus R1. That's it. That's it for my I1 coefficient. Let me go back to here just to add a little, perhaps more clarity. If I took this loop equation right here, I'm going to take this loop equation right here. And if I kind of organized it a little bit more, I would say, well, I have negative I1 R2 minus I1 R1. And then as far as I2 is concerned, I have plus I2 R2. And as far as R3 is concerned, I have plus I3 R1. And I'm going to bring this voltage over to the other side just because I want to do things methodically. I'm going to do the same thing every time. So this would equal minus EMF. So this is what I'm going to do in the spreadsheet. So I think I jumped to the spreadsheet too quickly because look at how I processed loop one, my loop one equation. And I just want to double check myself. I have negative I1 times R1 right here. I'm sorry, negative I1 times R2, done. Let me not use a green highlighter. I have negative I1 R2, done. I have negative I1 R1. Yep, there it is. I've got positive I2 R2. Yes. I've got positive I3 R1. Yes. And I brought this over to the other side, which means I subtracted it from both sides. So that's loop one. Let's do the same thing for loop two, just in terms of organizing things. This is loop one. Loop two, I'm going to keep track of things carefully again. Here's my I1. I've got I1 R2. So let's go ahead and record that. Plus I1. So this is I1 R2. I1 R2. Got that done. I1 R2 is now recorded. For I2, I've got a couple of things. I've got negative R2. Well, let me do it like this. Negative I2 times R2 minus I2 times R1 minus, and I guess that's it. Minus I2 times R3. Almost missed that one. And then plus I3 R3 equals 0. And let me double check. Here's I1 R2. I1 R2. Yep, I got that. Then I have negative I2 R2. Yes, I got that. I have negative I2 R1. Yes. And last but not least, I have negative I2 R3. Yes. And then last but not least, I have positive I3 R3. Positive I3 R3. Done. All right. So I am feeling good about loop number 2. This is loop 2. Last but not least, loop 3. I'm going to go through and tally everything up. It looks like I have I1 R1. It looks like I have plus I2 R3. And then as far as I3 is concerned, I have minus I3 R1 minus I3 R3 minus I3 R2 equals 0. And this is loop 3. Okay. And doing it, only the paranoid survive. So I1 R1 should be a positive. It is. I2 R3 should be a positive. It is. And then I have minus I3 R1. Okay. Minus I3 R3. Okay. Minus I3 R2. Okay. All we're doing, Ohm's law and the loop rule, and then organizing, being like crazy focused on organization. So these are my 3 loops. I'm going to bring these 3 loops into Excel. And I need to Excelify these. I'm going to take all 3 of those and go to Excel. Get rid of that. That was not quite ready for prime time. Here's all right, so this is what I need to do for Excel. All right, so I'm going to get rid of this. Here goes. Looking at loop 1, let me check. Did I cut something off? No. All right. Looking at loop 1, let's put loop 1 into Excel. All right, ready. Negative, so this equals, look at I1. Negative I1, if I'm looking at right here, I'm looking at negative I1 R2. So that equals negative R2, click, minus R1, click. Okay, and done. Done with that entry. Minus 3840 is what we should all have. And let me just check something. I want to just double check. I1, negative I1. Okay, I guess that's good. Okay, so let's keep going with the spreadsheet. I2, so now here's my I2 contribution. I2 is just going to equals R2, click, enter, done. Here's I3. I3 is just R1. Ready? Right there in that cell equals R3 and done. Last but not least, I brought my EMF over to the right side because that's just my standard operating procedure to keep track of everything. Equals negative, click. So right now, let's all use my numbers and make sure you agree with negative 3840, 2520, 3060, and negative 10.2. And if you don't, let's troubleshoot or talk, but we all have to be on the same page here. Let me just double check with what I did before. Negative 3840, 2520, 13. I made a mistake somewhere with I3. I3 equals, yeah, there's a mistake. Yikes. That's embarrassing, but better late than never. So I did make a mistake. So now we should agree. You should have negative 3840, 2520, 1320, negative 10.2. And let me just go back. Since I made a mistake there, I'm just going to redo it. I3, according to loop 1, I3 should have just been equals R1, click. Okay. All right. Let's do the same thing for loop 2. All right. Here's my I1 value. My I1 value is simply R2. So equals, be careful, R2, done. My I2, there's negative I2 R2, negative I2 R1, negative I2 R3. So ready? It's going to equal right here. Equal negative R2 minus R1, click, minus R3, click, and that should come out to be negative 6,900. Okay. I3 is just equal to R3 right here. I'm looking at I3, R3 equals R3, click. There's no EMFs, so this is just equal to 0. So let me check myself against myself. 2520, negative 6,900, and 3060. All right, so we should all have these numbers right here. This is how I'm putting this equation into Excel in matrix form, basically. Let's finish this. I3, or loop 3, I should say, loop 3. Ready? Well, I only have one I1 coefficient, and that's R1. So this equals R1. Click. All right. I2, I just have I2 times R3. So this is equal R3. Click. And then I have these 3 multipliers. So it's going to be I3. It's going to be I3. This is why I'm in the I3 column. It's going to be I3 times negative R1 minus R3 minus R2. So ready, equals. So what I'm doing now, I'm saying, hey, this is equal to I3, hence that column header, I3, times negative R1 times a negative R3 times a negative R2, and done. And there is no EMF there. And let me double check myself on this. 13, 20, 30, 60, negative 6,900. Okay, there. So this is a good pause point. We should all have exactly this. We should all be in agreement right here. Okay. So let me get a time check. All right. So let's do this. If you're good to go with that, now what we're going to do is do some matrix multiplication. I'm going to go into my notes here, my lecture notes for us. Here's the lecture notes, and this is what we're doing. So I want to just show this. I want to show you what I'm doing as I do it. All right, so mesh method is described right here. Basically, this is what you did. You basically just organized these simultaneous equations into a spreadsheet. Okay, so this is what you're looking at. Let me bring my spreadsheet. We've done this organization. I'm going to get rid of this since we're done. We've processed all that. This is what we're going to do now that we have the spreadsheet completely set up. We're ready to have Excel crunch numbers for us instead of us crunching numbers. All right, but this is the Excel that we all have cranked out. All right, so these are my currents. There's I1, I2, I3. Okay, those are my currents. These are all my resistor values right here, some color coding things. These are my resistor values. All of those were just the resistor. This is all just Ohm's law. And then these are all my voltage values right here. Okay. So what you're looking at is Ohm's law. Remember what Ohm's law is. Ohm's law says V equals IR, where this is I, yellow is I, there's my voltages, and green is my resistors. So again, you're looking at Ohm's law. This is my resistor array, this is my current array, and this is my voltage array. So it really is that straightforward. This is voltage equals current times resistance. Now, in this case, I know voltage, I know resistance, but I don't know the current, which is what we're trying to find. So current, if V equals IR, I equals V over R. Okay, so from a matrix point of view, this is how I'm going to deal with it from a matrix point, simultaneous equations. This matrix of current values, I1, I2, I3, is going to equal R inverse, the inverted R matrix times the voltage, like this. So up here, if I want to solve for I can say, well, yeah, I equals R inverse times V. That's what these are the same. These are the exact same expressions. And that's what I'm doing here. And this is a matrix. Okay. So here comes Ohm's law brought to you by a spreadsheet. Ohm's law, I'm taking, again, I'm just thinking this through. I'm isolating all of these currents. I'm going to figure them out by taking my inverted R matrix, R to the -1, which is, here's R to the -1. And then all I have to do is figure out, how do I invert that matrix? And then once I invert that matrix, how do I multiply it with my voltage matrix? So that's what we're going to do in Excel right now. All right, let's invert this matrix. So this is a 3 by 3, 1, 2, 3 by 1, 2, 3. So that's a 3 by 3. I'll color code this. Those are my resistor values. I want to invert this. Ready? Invert it. Give yourself a landing pad of 1, 2, 3 by 1, 2, 3. So is that clear? Is everyone clear on that? I have a 3 by 3, 1, 2, 3 by 3. So if I have a 3 by 3 and I want to invert this matrix, I'm going to have to give myself a landing pad of 3, 1, 2, 3 there. So my landing pad is the same size as my initial R matrix. I need to invert that. So I'm just, I'm hands off. I just highlighted those cells. And then with your hands off the keyboard and mouse, because those are just sitting there highlighted, now you can go to the keyboard and type equals minverse. Minverse. Minverse stands for matrix inverse. So this is how you invert this matrix in the world of Excel, in the world of linear algebra. Take those 9 values, let go of the mouse, let go of the keyboard. Once you highlight them, let go of everything, hands free. And if they're sitting there all highlighted, waiting to be inverted, don't close the parenthesis, hit Control Shift Enter. And there you go. That's my inverted matrix. So this is a key step. In fact, I'm going to repeat everything I just said. Hopefully you're okay. Hopefully you're following the math and physics behind this. Well, really, it's the math. I need to come up. I want to solve for those current values. I need to cough up. I need to invert my R matrix and then multiply it by voltage, because this is just Ohm's law after all in matrix form. So ready. I'm starting off with a 3 by 3, which means I have to give myself a 3 by 3 landing pad. 1, 2, 3, 1, 2, 3. So there's my 3 by 3, hands off. They're just sitting there activated. And then equals minverse. Left parenthesis, select the matrix you want to invert, all of that matrix. Don't close the parenthesis. You hit Control Shift Enter. Okay. And that is my inverted R matrix. And then we're almost done, and we will finish by 11:30, believe it or not. All right. So then, and again, this spreadsheet can be very reusable. Here's my array of currents. I'm going to color code those just to be easy to identify. Okay. And then here's my array of voltages, because all I'm doing is using the loop rule to crank out Ohm's law. There. Okay. So there you have my 3 matrices. This is my inverted R matrix. So now I'm just going to go over here and say, well, okay, let's talk about what the result's going to be. I1, I2, I3. Okay. Right, justify, I guess. So now I'm going to figure out what each of those current values are. Okay. So according to the math that we know, I need to take that inverted R matrix and multiply it by my voltage matrix. And when I do that, I'm going to know my currents. So let's go to spreadsheet. As said, I'm going to take my inverted R matrix and multiply it by my voltage matrix. So give yourself a landing pad. 1, 2, 3. There's my landing pad. All right. So first things first, type in equals MMULT. MMULT stands for matrix multiply. So equals MMULT, left parenthesis, take the first matrix that you want to deal with, and R has to come first. You don't have a choice. R must come first. So there's my inverted R matrix, comma, And then here's my voltages matrix, my voltages matrix. There they are. You don't hit close parenthesis. You hit Control Shift Enter. And there you go. And let me just check myself against myself. 55003 0024. All right, so let me repeat that. I'm saying, okay, I've massaged everything. I've been a good scientist, engineer here. I want to give myself a landing pad for those 3 currents. And I'm going to say, okay, once again, just to beat a dead horse, I'm going to tap into this expression right here. I'm going to do this in Excel right here. I've already inverted my R matrix. I'm going to multiply it by my voltage matrix. All right, so here's how we do that in Excel. There's my landing pad equals MMULT, left parenthesis. This is my inverted R matrix, comma. What's next? It's the matrix I want to multiply that by. My voltage matrix. You don't close the parenthesis. You hit Control Shift Enter, and we're done. But we're almost completely done. But let's change precision. Let's go with scientific notation 5, I guess. So activate every cell in the spreadsheet and change your number, format your number so you get scientific notation 5, or let's just go with 4 for now. Scientific notation 4 for now. Okay. So you know you're done. We know we are completely synced when we all agree on these numbers right here. So this is the validity check right here. Let me validate myself. Let me take a snip. This is what I got from before, and I verified this with falstad. So I'm just going to sort of do a copy and paste to just, again, verify myself. 55203, 55203, 30927, 2427. So that's it. So I verified myself. So now all you guys need to do is make sure you completely agree. Keeping my eye on the clock, and we're good on time. I can repeat any part of this, but as complicated as you might think this is, if you step back and look at the big picture, this is all you did. You basically said, hey, I'm going to use the loop rule. I'm going to follow Probert around these loops and just use Ohm's law to tally everything up. You got 3 simultaneous equations. And we said, well, if we organize things the right way, we're going to be able to jump to do this in Excel. So I got 3 simultaneous equations. I sort of organized them like right here. And it was this organization right here that we put into Excel. Believe it or not, this isn't that daunting. It is right now because it's new and crazy. But if you guys are good to go on this, we just jump into falstad, and let's whip this up very quickly in falstad. We're going to finish by 11:30 because I never want to go overtime. That would just be rude. So let's go into falstad. Falstad circuit simulation. Let's go falstad, full screen, blank circuit. And let's just quickly whip this up in falstad. And this can go fast. All right, so I just have that diamond shaped thing. So here goes, resistor. There's a resistor. There's a resistor. Here's the bridge resistor. Then down here. And then close it. And then I have a battery. Battery. Okay, battery. And then close it off with some wires. Wires. We're done with the circuit. The only thing I need to do, I'm going to put a ground here. Did it show a ground? It didn't. So I'm just going to put a ground right here. Right click, inputs and sources, add ground. So let's just put our little inverted tree. That's the reservoir. Reservoir, this ground means if you get a surge in electricity, this will absorb the surge. If you have a shortage of electricity, this will provide it. All right, so now we just have to do the values. The battery voltage was 10.2. So let's go 10.2 for the battery voltage. 10.2, done. All right, top left resistor and bottom right resistor. So top left resistor and bottom right resistor is R2, that's 2520. So this is top left is 2520. Bottom right is 2520. Those are matched in this case. 2520. Okay, so back to bottom left and top right, that's R1, and that is 1320. So back to falstad, 1320 for bottom left, 1320, 1320 for top right, 1320. The bridge resistor is R3. R3 for me and for you, we're all using these same numbers, 3060. 3060. Okay. And I guess that's it. So what I have here in falstad is exactly the same as what I have in Excel, which I solved using math and physics and spreadsheet. Let's verify it. So if I go to Excel, my Excel is saying current I1 is 5.52 milliamps, 5.5203 milliamps. Where's current one again? This is where you're drawing. Loop current one is right here. This is loop current one, that's left current. So my Excel is saying 5.52 milliamps and some change. So if I go into falstad and I put my cursor anywhere right here, there you see it, 5.52 milliamps. So that I1 in falstad is agreeing with I1 that we came up with using math and physics and Excel. Let's verify I2. I2, this is I2 right here, different color. I2 is this top right current, I2. So I2 from my work, from your work, according to math, physics, and Excel, that should be 3.09 and some change, 3.093. It's probably going to show up as 3.093 milliamps in falstad. Let's look at I2, which is this branch. This is the top right, 3.093. The last check we need to do is this bottom right. From our drawing, bottom right is right here. This was the bottom right loop. The bottom right loop, I3, according to our math, physics, and Excel, this should come in at 2.43 milliamps. Ready? Here's the check. 2.428. So we got another precision. 2.428. My spreadsheet said 2.42. If I rounded 2.428 as well. So we have complete agreement. You should save this spreadsheet for posterity. It's going to get a little bit bigger, but it's not going to get too much fancier. So right now, you need to open up another Word document, and I can preserve the header. All right, so here's your Word document. Let's do a snip. So I'm not gonna count quiz 3. I'm gonna count this as quiz 3 since we're out of time. I'm gonna hit the escape key, switch from construction mode to just select mode, move things down here. And now we should put let's put our cursor on that top right resistor, the one that showed 3.093 milliamps of current coming through. Then you can do your snip of that, snip, and then take a screenshot of that. And we all have to have the exact same numbers down to whatever decimal place we're using, because this is getting shipped off to other reviewers. So there. All right. So good. So you can paste that right here. And now this will be chapter 27 quiz. And this is falstad. I got to check what problem this was. This was problem 2735. So this is 2735. So update your header. This is the new header. This is your pasted falstad circuit, which is perfectly agreeing with your Excel, which was created via math and physics. And then I'm going to